Hey everyone, welcome back. If you're gearing up for the Cambridge AS and A-Level Computer Science exam, specifically Syllabus 9618, you absolutely need to stick around. Today's explainer is all about a topic that literally trips up thousands of students every single year, star topology. But hey, we're not just going to sit here and memorize textbook definitions. No way. We're treating this explainer as your ultimate strategy guide. We're going to crack open the exact academic blueprint that examiners use to grade your papers. That way, you'll know exactly how to structure your answers and secure maximum marks. Let's get right into it.
Take a look at this, 15%. That is the massive weight that star topology questions hold in Paper 2. In the high-stakes environment of A-level computer science, 15% is, well, it's frequently the difference between two entire grade boundaries. It's literally the difference between an A and a B, or a B and a C. So this isn't just some minor subtopic you can quickly skim over. This is a huge opportunity to lock in a massive chunk of your grade if you know exactly how to play the examiner's game.
And you don't just have to take my word for it. Listen to this quote directly from a senior examiner. Did you know that star topology advantages and disadvantages accounts for approximately 15% of the total marks in Paper 2 of Computer Science 9618? See, we're building our entire blueprint today based on these actual, real-world insights. When the folks who actually write and grade the exam tell you exactly where the marks are concentrated, well, it's definitely time to pay attention.
Okay, here's our agenda for today. 1. The 15% secret. 2. Theoretical foundations. 3. The technical methodology. 4. Critical analysis. And 5. Top examiner traps. Let's do this.
Section 1. The 15% secret.
So, capturing this huge portion of the exam requires a really specific approach. Raw memorization, it just won't cut it here. The real secret to unlocking these marks is what we call the method mark strategy. Basically, examiners award marks for the process, not just your final answer. For example, you might know that a star topology is entirely dependent on its central switch. Great, but if you don't show the logical, step-by-step process of how a switch failure specifically causes a total network bottleneck, you're going to drop the majority of the marks. They want to see your brain on the page, plain and simple.
Moving on to Section 2, Theoretical Foundations.
To actually show that methodical process, you need a rock-solid foundation. At the 9618 level, the assessment heavily prioritizes analytical depth over just superficial breadth. So let's walk through the core theoretical principles. First up, logical reasoning. Your answer has to flow seamlessly. Second, precise definitions. Instead of saying something like, the computers break down, say the individual nodes are isolated. See the difference? Third, causal relationships. Explain the why. For instance, how does the physical setup, where each node has its own cable to the hub, cause an advantage? Well, it means one broken cable won't crash the whole system.
And this brilliantly illustrates our next major point, cross-topic connections. Principal examiner reports explicitly state that candidates who connect the dots with other syllabus areas achieve significantly higher marks. So don't view star topology in a vacuum. Ask yourself, how does a central hub's single point of failure impact network security protocols? Or how does the heavy cabling requirement relate to hardware budgets? Weaving these other concepts into your answers proves you've got a truly holistic understanding of computer science.
All right, Section 3, the technical methodology.
When you actually sit down in that exam hall and face a really complex scenario, you need a systematic process. Treat this highly structured 5-step progression as your ultimate exam toolkit. Step 1. Deconstruct the question and identify the command word. Step 2. Extract the relevant data from the scenario. Step 3. Select your analytical framework. Step 4. Execute with clear notation. Show all you're working. And Step 5. Present your final answer using precise terminology. Honestly, this framework works for literally every complex question they can throw at you.
Now, when you're applying these methodologies, examiners are really testing your algorithmic thinking. This means step-by-step decomposition of the network problem. If you're asked to program a network simulation, it means selecting the appropriate data structures. Data interpretation is absolutely critical here. You might be asked to pull information from binary representations or perform exact calculations for data transfer rates across those heavy star topology cables. You just have to be incredibly methodical.
Which brings us to Section 4, Critical Analysis and Evaluation.
This right here is the highest level cognitive domain assessed in the syllabus. It's where the top students completely separate themselves from the rest. A huge requirement here is comparative analysis. When you're evaluating star topology against, say, a bus topology, do not just list facts side by side.
You have to actively identify similarities and differences using comparative connectives. So, for example, a star topology requires significantly more cabling, making it more expensive to set up, whereas a bus topology is cheaper but conversely lacks the fault isolation benefits of the star. When evaluating algorithm quality or system design within a network, examiners are looking for very specific metrics. You've got to analyze time complexity, like how efficient is data routing through that central switch over time. You have to address space complexity, which is all about memory resource requirements. You must look at edge cases, what actually happens under extreme operating parameters. And finally, the performance effect. How do all of these elements impact the overall system?
To summarize this evaluative stage, I really want you to internalize this problem-solving flow. Think of it as a continuous loop. You deconstruct the given information, break it down into logical steps, solve it systematically, check the reasonableness of your answer, and finally, make justified recommendations based on the scenario. This deconstruct, solve, evaluate loop absolutely guarantees the kind of logical reasoning that examiners crave.
Finally, Section 5. Top examiner traps.
Welcome to the autopsy portion of our explainer. We've combed through the Cambridge Principal Examiner reports, and we found 3 critical, repeating mistakes that literally cost students whole grade boundaries. Honestly, it's kind of surprising how often top students fail simply because they panic under exam stress and forget the most basic edge cases.
Let's rapidly break down these 3 examiner warnings. Trap number 1. Using the wrong algorithm for the specific network context provided. Trap number 2. Forgetting to check boundary conditions and edge cases. I mean, what happens when the central switch reaches absolute maximum capacity? Students often only explain the normal operating state. And trap number 3, which is honestly the most fatal of all, providing generic answers.
I cannot stress this enough, so listen up. The classic mistake is a generic answer. If the exam question is about a star topology in a hospital network, and you just write a central hub connects all nodes, you are going to lose marks. You must be specific. Say, the central hub connects all hospital ward workstations to the main patient database. See what I did there? Always link every single point you make directly back to the specific scenario they gave you.
Which brings us to the end of our explainer, and I want to leave you with one final question. Will you fall into the trap of generic answers, or will you secure those massive method marks by linking every theoretical concept to the specific exam scenario? You now have the frameworks, the methodological steps, and the inside examiner insights to capture that crucial 15% of Paper 2 dedicated to star topology. Take these evidence-based strategies, apply them to your next set of past papers, and watch your final grade reflect your true potential. Thanks so much for joining me, and keep learning.